just to say, I'm usually I'm a Linux user, and so I didn't bring my Linux laptop because but actually it didn't work anyway. So probably it's more about being a Linux user and somehow is it's a kind of magical thing going on. So today we are going to talk about AtomVM. And before starting talking about AtomVM, let's introduce myself very briefly. So I tinker with hardware since 2004. It's quite a long time, both on the hardware part, but mostly on the software part. And also, when I was a student in high school, and since then, I always been passionate about open source software. So at a certain point, I created AtomVM. And it was in 2017, is that the year that I discovered Elixir, because I fell in love with Elixir. And yeah, the first question is, what is AtomVM, of course? Well, probably you know that because they did a lot of spoilers. So, well, I try to maybe add some kind of different point of view anyway. So, before answering this question, we need to take a time machine and go back in 2010. And in 2010, people were talking about physical computing. And physical computing, compared to the traditional computing, is all about interacting with the physical world. So you don't have screen, mouse, or keyboard. You have LEDs, motors, sensors, buttons, and etc. So the idea of physical computing is just interacting with the physical world. And so Arduino was very good at it because it had a very, very cool IDE. And the board, compared to other solutions at the time, was very cheap. It was not that cheap like today, but, well, it was cheap for the time. And it was very powerful because it had something that is called GPIOs. But still, if we look at the core, we will notice that it has an 8-bit CPU. And it has very few kilobytes of RAM, very few kilobytes of flash memory. But it was still possible doing a lot of different stuff. And things have evolved eventually, and people started to talk about Internet of Things. And when you have to talk about Internet, you have to deal with payloads, with packets, and you need more memory. So everything got more, there was a remarkable evolution. And devices got cheaper, but also more powerful, like this one that has some megabytes of RAM. Well, the basic model, few hundred kilobytes, but you can have enhanced version, a few megabytes of flash, and also you have, like Arduino did, a number of GPIOs. You have, compared to Arduino, you have connectivity options and so on. So there was this kind of remarkable evolution. Still, we are very, very far away from what we are used usually. When we think about a workstation or even a mobile phone. And there are some differences that are very important. And the most interesting one is that you don't usually have an operating system. You have something that is called real-time operating system, but is basically a scheduler. You don't do anything else, basically. And also, the other thing is that usually, most of the times, you work with C or C++. And if we think about C and C++, if we think about the hardware I just mentioned, you have two cores. And when you have two cores, you think about concurrency. And when you think about the concurrency with C, you end thinking about mutex, locks, spin locks, and all that stuff that can be very tricky to work with. And also, if you think about data coming from sensors, you can think about parsing data. Parsing data in C, in the best situation, is just boring. But if you deal with an untrusted input, you have security concerns. That is a problem. And also, if you need to deal with some kind of remote API, you have to do a lot of asynchronous stuff. And if you do asynchronous stuff with C language, it gets very easily into some kind of asynchronous spaghetti hell that is not very nice to deal with. And the most known issue is memory management. And memory management can be very, very a big issue, because in the best situation, and I remark that best situation, I said, you have a crash. But since you don't have an operating system, you can frequently end into some kind of silent corruption that might appear or not later. And also there are some more well-known issues like memory allocation. So you end asking yourself, did I free that memory? And usually the answer is no, you didn't. And as I mentioned on the first slide about myself, I love hiking. And there is a project that was like, it was interesting for me because it is called Meshtastic. And Meshtastic, I'm taking this as an example, by the way. It is not the purpose of AtomVM itself. But Meshtastic is about building some kind of mesh network, and it has routing, it has message encryption, and a lot of interesting, cool features. And it allows you to communicate over some kind of long-range radio with other people doing hiking with you. And it is a very clever project, very remarkable. And if you look at the source code, it's a very huge code base written in C++ that runs on that limited hardware. I mean, that device is an Espressif 32, the one that I shown you before. And so those developers didn't have any other option than writing a lot of C++ code. But let's think about what we can do in Elixir just for a moment. And if we think about parsing binary data, if we think about Elixir, this can be done in a very, very clear way. And the whole parsing logic can fit just this slide. That is very remarkable. Still, there is some kind of important point here. Meshtastic developers didn't have any other option because the C and C++ was all they had available. So the question is, do we have any other way that allows us to use what we love, the tools we love, the ecosystem we love, the features we love in such constrained environments? And my answer to this was AtomVM. So basically, I created AtomVM from scratch. That means that I didn't use any actual source from the beam. It's written completely from zero and with different design goals. My design goals were making use of, saving every possible kilobyte of RAM. It was making it easy to adapt and port to different hardware or different operating systems or different platforms in terms of hours of development, not days or week. So it had to be very flexible. And yeah, if we get back to the example, lately I've been doing this kind of proof of concept where I did some kind of replacement firmware that is written in Elixir. They are very few lines of code, and you can do pretty the same stuff. I mean, you have a user interface, you can type messages, send messages, or receive messages. But the code base is very clear, and the whole software is also reactive in such a remarkable way. And we are running on the same constrained hardware. That is super cool. And yeah, this is the proof that it is possible to do what we wanted to do. And yeah, I'm not going to tell you to start with such a complex project. It's not that complex, honestly, but it's still more complex than Hello World. And I want to tell you that you can also do physical computing, and doing that can be very simple and can be a funny activity, actually. And we can start with a usual Hello World. And so before starting, you actually need to buy some hardware. So there are several different options. And I'm going to tell two well-supported options now. So the first one is Espressif. Espressif makes some very cheap development hardware that you can buy in different flavors. Some of them have Zigbee, some other don't, some other have Wi-Fi. You can pick any according to your taste. And also there are some kind of ready-to-use development boards that one is the cheap yellow display that has been popular lately, that has a display, you can display stuff, have some kind of touch screen or whatever. So it can be very cool. And the other option is the Raspberry Pi Pico, that is the limited zone of Raspberry Pi. So it has fewer resources, and it has less memory, but still it is super powerful. Also, it has something called programmable I/O, that is kind of an engine for making some very clever tricks with I/Os. And as soon as you get your hardware, you need to make some kind of basic setup. But it's super basic because you just need a USB cable, a serial monitor software such as Minicom, and mostly you need your usual development setup. You don't need anything special, actually. And here there is the first big disclaimer. The first big disclaimer is that I will show you some steps, but those steps are about a project that is evolving. So what I show you today eventually will change in a good way, hopefully. But still, the concepts I will show you will remain the same. So if you take a look to our documentation, you can stay up to date and know how you can update your project and also how the concept will change. I mean, the API will change. Also, there is a further disclaimer, and I will show you, also because we have limited time, how to do this with Elixir, but the same stuff can be done with Erlang. There is a Rebar-free plugin, and also you can do this with Gleam. I'm not a Gleam expert, but I know there have been some work. Anyway, if you want to work with the Elixir, you just have to add a dependency to your Mix project file. And as soon as you add that dependency, you can start with the first command that allows you, if you are using expressive hardware, to download a pre-built binary and to install it on the hardware. So you don't have to worry about anything else. You don't have to install a toolchain or a SDK or a C compiler. Just that command is enough. Next. The next step is configuring your mix file. You just need a couple of information here. One is telling which is the entry point and where it is going to be written, and that's it. And as soon as you do that, you are ready to make your own hello world. And hopefully this is pretty clear. I mean, I think it's kind of easy syntax, and well, there are some easy APIs to use. And the only thing that we have to talk about very briefly is what is a general purpose input-output. And basically, general purpose input-output is a pin you can configure in a flexible way. So you can choose either if you use it as an input or as an output. And when you use it as an output, you have only two possible logic levels that usually they are 0 volts and 3.3 volts. And that's it. So you cannot do any kind of fading or anything else with your LEDs. There are other options, of course, but still, this is what is a general purpose I/O. And so going back to the workflow, as soon as your code written, you just need to flash it in order to run it later. And we have also a command coming from AtomVM for that. And as soon as you do that, we are ready for a demo. I'm not going to do any kind of demo, but you can use your own imagination for imaging a blinking LED. And yeah, we did that. And also, if you need to watch the debug messages, as I mentioned before, you need a serial output, monitor like Minicom. And that is pretty useful as soon as you start doing some more complex stuff, because debug messages are useful, you know. And yeah, that's it. You are ready to have output in two different ways, blinking LEDs and serial output. But before moving on, let's give some circuit pro tips. And I have 4 golden rules that save you some money. And the first one is never mess with ground, because if you have a ground pin, connect it just to ground. And the second rule is that you have to respect polarity, because you cannot reverse components. And the third rule is never mess with voltage levels. So also the most simple configuration, such as an expressive, has a 5 volts pin, and that one can fry your 3.3 voltage components, so be careful. And the third rule is widely less known because it's about antennas, but basically you never connect an antenna before, you should connect an antenna before powering on your device, because you should never transmit data without an antenna connected. Otherwise, you will damage the radio component. And all these rules can be verified in a very simple way, that is double checking everything before powering on the device. That is what really saves you money, time, and whatever. And yeah, we can move to the standard input, because again, we are in the physical world and our standard input is a button usually, or a sensor, but let's start with a button. And there are two options. The trivial one is like having some kind of busy loop, reading the digital value from that pin, but it doesn't work well. But you waste energy, CPU time, and whatever, and you have interrupts. But interrupts are when you stop software for executing other functions. But this doesn't really work nicely with the Erlang world. We have messages that are way better. So we do this also in AtomVM. So if you want to handle your button press, you just need something like a gen server. You can do your usual handle info and handle that button press. Super easy, hopefully. And yeah, we have standard input, standard output, and what we can do now. And peripherals is the answer. So if you have some kind of more complex sensor, maybe a display or anything else, you need to worry about buses. That means a bus is basically when you have several wires that allows you to connect multiple devices on them, usually multiple devices. And you can choose the bus according to your preference or configuration, but you also you have to look at the datasheet, because some sensor or devices have very specific buses that are supported. But the important point here is that our Erlang APIs, well, Elixir as well, and as far as I know, Gleam APIs supports all of them. I mean, the main buses. So if you need SPI, I2C, UART, or whatever, we have APIs for them. And they are completely, you can use them from Erlang, so you don't have to mess with C code, and you can even make some complex drivers, and you can just forget about C language. But sometimes, as we do in the Beam world, we need some kind of extra performances. In that specific situation, if you have those requirements, you can make some native components, and you have two options, basically make a NIF or a native port. But the important thing here is that we don't have dynamic loading, we don't have plugins, because you don't have an operating system, and you have to compile everything together with the virtual machine. That means you need to set up some kind of build environment. And that is the most important thing. And speaking of native ready-to-use components, we have a ready-to-use component for displaying stuff, that is AtomGL. AtomGL does all the work for displays, for a number of displays, and hopefully the number of supported displays will increase in the future. Anyway, what you have to do is basically pushing to that display a list of items that are basically some tuples with some properties. And yeah, you can display stuff as well. But we've been talking about Internet of Things, where is the I, and well, we have support also for internet stuff, and for that purpose we have the usual APIs you are used to, like GenTCP, GenUDP, and whatever. But also we have a number of additions, and we have support for HTTP server or request, and also stuff like MDNS for being discoverable on the local network. And speaking about making a web server on a microcontroller, it can be a very easy task. I mean, you need just few lines of code. On one side, you just set up it as a Wi-Fi station you connect to an access point, and on the other side you just bring up a web server and you wait for events, basically. And so I introduced right now some kind of extension to the standard beam because stuff like MDNS or the HTTP server we use, it's not part of the standard beam. But we have other difference and addition. One of them is that we don't ship to the device just the beam files, but we pack everything in something that we call AVM file. That kind of file format also supports assets. So if you want to ship some kind of CSS along your HTML, you can pack it together inside of those AVM file. The purpose of those AVM files is basically you don't require a file system or your Flash. It's something that it's very Flash friendly. Also, we provide some function, as I mentioned, for mapping to memory, so we don't even copy stuff to memory, so everything is in place from Flash, like read prev. And we have other extension. What I really want to tell you is that all our extension or addition are prefixed with AVM or AtomVM prefix, so you are always aware when you are using something that is not available on the beam. We want to be clear about this. And yeah, I've been talking of, as I mentioned before, constrained environments. And in a certain way, there are other kind of constrained environments, that is the beyond part. And as you may know, it has been presented in May, Popcorn. Popcorn is basically a library that allows you to bring your Elixir application to the browser. And the secret about this is that you actually have AtomVM compiled for WebAssembly that runs on the browser, because as I mentioned, the browser is a kind of constrained environment. And also, using AtomVM allows you to have a very, very small footprint in terms of download size, because it's very small virtual machine. You don't have to download tens of megabytes of stuff. And as soon as you start using Popcorn library, you have a number of mixed tasks and also modules that allows you to build your own web application. So it's pretty simple. And how you can do that? Basically, you just add it to your dependency. And as soon as you do that, you are ready to start with Popcorn. And if we want to think about what you can do with Popcorn, this is a very simple example. This is a game of life where every single cell is a different Elixir process. So every single cell is an Elixir process running inside AtomVM, running on the browser. And there is another cool demo, my favorite one actually, that is the wall EX shell running on the browser. So you can even try Elixir without having to install it locally on your computer. That is super cool. And yeah, I have some closing words about AtomVM. And there is some kind of recurring question that is, what is the difference with nerves? And well, it's a kind of apple and oranges comparison, because on AtomVM side, you have an entire virtual machine, not just a framework or some tooling. You have an entire virtual machine. But still, if we want to do this comparison on the embedded side, we have to remember that AtomVM is focused and targets devices that are very limited, as I mentioned. Also, they are usually very, very low power. And as an example of what we have been able to do, well, Paul has been able to do is La Machine. La Machine is a device, well, that runs Erlang inside on a very tiny board. And this tiny board has something like 5 microamperes of power consumption when in deep sleep. That is super remarkable and super cool. And yeah, it has several features. It's super cool. There is a talk about this. And it also plays audio, by the way. And let's talk briefly also about what's next. And what's next? Well, let's talk about recent additions. Recently, we added this year a number of cool features like Erlang distribution. And we introduced and we presented yesterday the just-in-time compiler. but also we introduce big integers, so you can, well, mostly big integers that are limited to a reasonable number of bits. And also what's going on next. We are going to support bit strings. I don't mean binaries. I actually mean bit strings. That, I mean the odd size one. And in the future, after this, we are going to focus on supporting more platforms. We are going to focus on a better developer experience. That is the reason API will change in a better way. And also, we are moving towards some stable APIs, so in the future, you will not have to worry about how things have changed lately. And talking about releases, you have two options. The stable option, that is, well, they are both stable in a certain way. Also, main is pretty stable. But you have the v06 option that has periodic updates, so we do some kind of maintenance releases, and it's pretty well tested. And also we have main that sometimes can be a roller coaster, but a good and nice roller coaster, that where it is where we add all the latest additions, like I mean the just-in-time or Erlang distribution, and everything has been made possible thanks to contribution. And we are a small team, but we are looking for any kind of contribution. We are not just focused on code contribution. You can contribute also helping community, or helping us to triage issues, or testing stuff, writing tutorials, anything you can think of. Any kind of contribution is very welcome, by the way. And also, I would like to get in touch more with Gleam people to make sure that also Gleam is more a first-class citizen in the future. And yeah, so in order, if you want to join us, we have different, communication channel. Everything happens mostly on Telegram, the development team, but also we are active on Discord. And well, if you want to know more how to contact us or about how to use everything, there is some good documentation there. So thanks.
Thank you. That was absolutely amazing. AtomVM scaling from like 0.5 megabyte of RAM to running in WASM in a browser that manages to take all your RAM. Any questions? Yeah.
So I guess to be able to squeeze everything that's in the Beam and the Erlang runtime system into this memory footprint, you would have to lose some things. So what's not there?
Well, by default, for example, we don't do just-in-time, and you cannot enable it. But if you go for emulation mode, you use a memory. Sometimes when we have to choose between different data structures, we go for the one that is more memory conservative and stuff like that. So we do this kind of decision when we have different options. And yeah. And also when we store terms, we try to pack everything. And by the way, I would like to also say thanks for the Beam book that has been very useful, especially in the first days. And this project is also possible thanks to the Beam book.
So I have a software running on ESP32 that is supposed to control our furnace, and it's written in C++ because that's what I had. And everybody advised me to try Rust because that's safer, because one of the problems, of course, I have is occasionally it crashes. So I'm really hyped about the AtomVM, and I want to try it out. Can you give me some kind of ballpark figure about the overhead I'm going to incur? And also I would like to understand, maybe can I simulate the hardware and try my code out without flashing it and see if how it would interact?
Yeah, interesting question. So the overhead question is kind of difficult question because it depends a lot on what kind of data structure you use, how you store things on memory, how many processes do you mean to spawn. But the hello world, the basic hello world, takes like 30 kilobytes of RAM. So just to bring up the atom table and few other structures. But as soon as you have that basic footprint, you can, increase the complexity of your application, and you can do fairly complex stuff. I can run a display demo with some graphical items on the 500 device. So with 500 of kilobytes of RAM, I can already do some interesting stuff. But it really depends on how you structure your code. And yeah, for my idea on the long term will be running and simulating some kind of device on a web browser, so you can have some kind of graphical, maybe environment to test stuff. But we are not yet there. It takes time to write some kind of environment. And if you want to have some kind of complete emulation, there are some good emulators. And also, since we have a functional language that is very well testable, you can write all your tests, or even you can run everything on Linux, so you can have your computer as a test environment. You don't have the full device, but you have something very reasonable.
I have a question. What does configuring the hardware abstraction layer kind of look like in practice? Is it something that involves getting to the C side, mapping pins and GPIO, or is there something more abstract for managing that?
Depends. Do you mean when you do the porting, or when you
porting to like some unusual device that you may not
well,
support yet?
Well, when you do porting, we have a few functions that have to be adapted to the new target, and mostly these functions are about time and timers, because you need the scheduler working, and maybe also about threads. But it's not. You can also do a single core implementation, and then you have to write bindings basically. And also memory mapping for the program. But it's pretty straightforward. We have some kind of simple platform. But as soon as you do the porting, everything will be very smooth, because you just care about writing Elixir code. And if you use the well-supported platform, you don't have to care about porting. And what I really hope for is supporting Zephyr. As soon as we have Zephyr running, we can support a very, very vast number of different devices, thanks to Zephyr, that is kind of abstraction layer plus an RTOS.
Is the bus interface the same for nerves and AtomVM? So can I develop on nerves and talk to an I2C device and then just use it on AtomVM?
No, they are not the same. Actually, they are somehow similar. My personal plan, but we have to discuss this, is to make maybe the Elixir part closer to nerves, so we can allow some porting. But this is something that still has to be done. But it is one of the things that we really want to investigate. Also, if we think about, as far as I know, there is no nerves for Erlang or Gleam. In that case, the API is completely, different.
All right, thank you.
Thank you.